Alright, so in this lecture we're going to talk a little bit about plates. Now the intention for this is to be part of a course in theory of elasticity where we do some examples, in particular specializing our three-dimensional equations of elasticity to 2 dimensions. But I hope if I get a chance to dig into things a little bit deeper, then I can use this as a starting point to take a look at maybe eventually shells and orthotropic plates and maybe even composite laminates. So in this section we're going to specialize general strain displacement equations for small strain elasticity for two-dimensional plate analysis. We're going to take a look at stresses and strains and curvatures and vertical displacements among other things. And we're going to start with an isotropic material that's linear elastic with an unstrained midplane. And again, like I said, as we get into these other areas, we'll relax some of those restrictions and look at midplane strains and so forth. And a lot of this analysis on the plates is going to end up following the book that I used a while back, Stresses in Plates and Shells by A.C. Ugerol. So let me put a little plug in here for that book. There it is on Amazon. That's the edition that I've got, and it's pretty cheap these days, a few bucks. But before we get into that with all the plates, I just want to have this brief lecture to review what we know about beams already. Now I teach a class in mechanics of materials, and I have all the details listed there for beam theory and displacements and stresses and all of that. And plates are very similar. However, there's a little bit of a difference in that a lot of people use a different coordinate system than what most modern mechanics of materials books use. So the first thing I'm going to do is just to restate everything we know about beams in a typical plate type coordinate system, and we'll see about the deflections and stresses and strains and so forth. Alright, so beams and plates share some similar features in their analysis methods and equations. So we're going to review beams, and in fact if you were to take a plate theory and reduce one of its dimensions to be very small in comparison to the other, it'll basically give you the beam theory back out of it, or pretty close to it. So let's just start off with our beam, and let me draw just a rectangular shaped beam. And we'll have a neutral axis that I'll dash in here. That will be the location of zero strain on our beam. Now initially we're going to just take a look at pure bending. So that will be right at the centroid location of our beam. And that's something that we go through and we show how that works in mechanics of materials. Our coordinate system is going to be located then at the neutral axis, and for elastic material behavior corresponding to the centroid, we'll have the x-axis down this way. We're going to take the y-axis this way, and the z-axis will be down in this direction. So we will follow the Euler-Bernoulli restrictions. And basically, so as I mentioned, pure bending. We're going to have a prismatic beam or a constant cross section. And for our purposes, this cross section is going to have a vertical line of symmetry. And so maybe like a T-shaped cross section, something that if we had draw a vertical line through the middle of it, it has that as a line of symmetry. Let's first take a look at the strains that develop in a beam like this. And we'll look at those strains by taking a look at this sketch. So here I have a section of undeformed beam. I have a few points on here. Those are represented by those dots, and those points are initially a certain space apart, delta x apart. But the second set of points down here, a little bit lower, are on the positive z side of the axis, and they're at an arbitrary z distance that lies through the depth of this cross-section. We can imagine some bending moment applied to this that bends this beam downward, and it turns into a section of a circular arc. So there's some radius of curvature here. It describes the locations of these points. And so here's the points that are on this arc that were originally on the neutral axis. And then these points that are down below the neutral axis, they have decreased in their length just a little bit. Now for reference, I'm going to call the distance from the center of curvature to the neutral axis the symbol rho. We're also going to call that r a little bit later on. And so the distance from the center of curvature to these 2 points down below the neutral axis are going to be, that's going to be the distance rho minus the distance z. And so these 2 points down here, they were right below the center. They were delta x apart. If we wanted the strain, then it's the final length, we'll call that arc length delta x star, minus the initial length divided by the initial length, just based on our engineering definition of strain. Now our initial length we can find from this picture right here. Delta x is rho times this angle, we'll call that delta theta star, that's in between. And the new length of this segment is the distance rho minus z times delta theta star. So if we put these in here for our longitudinal strain, we're going to get, let's see, rho minus z delta theta star. We're going to get minus rho delta theta star. And then we're going to divide this by rho delta theta star. And so a lot of things cancel out. The minus rho delta theta star cancels out with one of them on top. We're left with a minus z delta theta star, but the z stays on top, but the delta theta star cancels out on the top and the bottom. So our strain is equal to minus z times z over rho, where rho is the radius of curvature. Now there's another term I'm going to introduce at this point. It's called the curvature, not the radius of curvature, but the curvature of the beam. It's going to use the symbol kappa, and it's defined as 1 over the radius of curvature. So another way to write this is the longitudinal strain is minus z times the curvature. Alright, so that's how we get the longitudinal strains. If we are restricting ourselves to a linear elastic isotropic material and can assume that we have essentially a uniaxial stress state in our beam, let's write some of that down. Then sigma in the x direction is equal to E, the modulus of elasticity, times the strain. And we can write this as minus z E over rho, or minus z E times the curvature kappa. Let's dig into the stresses just a little bit. We can look at the side view of our beam. Here's our neutral axis. What this equation describes is a linear distribution of stress from the neutral axis. Z being positive downward, the negative sign of the equation putting compression on the bottom, and z being negative on the top with a negative sign in the equation, canceling themselves out to put tension on the top. Okay, and so that's when we have our moment that goes in this direction. In a three-dimensional view of this, you can imagine there's this triangle here that tapers down to the neutral axis. It takes kind of a wedge shape. And then there's another triangle. Oops. There's compression on the bottom that tapers in magnitude back that way. If we identify a small square of material, at that particular spot we have that stress sigma x. But also around this area, if we call that area dA, we can identify a little bit of force that acts at that spot. So a little bit of force in the x direction is going to be equal to the axial stress sigma x times dA. If we want to relate that to the moment is going to be equal to the stress times the area, the force, times the z distance. Now, I've already drawn this arrow in the correct direction that accounts for the sign of that. So in this next equation, I'm just going to look at the magnitude. But then the moment is going to be equal to z, oops, this should be z dfx. Correct that here. Z dfx, or z sigma x dA. Right, so the moment is equal to z sigma x. A little bit of the moment is equal to d sigma x dA. If I want the entire moment, I have to integrate it over the area. So I have sigma x times z dA. But I know what my equation for sigma x is. My sigma x equation in magnitude is z e over rho. So that means that my moment equation is going to be an area integral of e over rho times z squared dA. Now the e and the rho are assumed to not be dependent on the in-plane dimensions, the y and the z dimensions. So we're going to remove those from the integral. And we're left with an area integral of z squared dA. And what that is a moment of inertia term. So we have what's known as the moment curvature relationship. M is equal to EI over rho, or EI times kappa. Alright, so let's write down some of that. M is equal to EI over rho. We also know that sigma, with the sign in it, is minus z e over rho. We rearrange the first equation. We have rho is equal to EI over m into the second equation. Then we would have sigma is equal to minus z e, and then we have on the bottom EI over m modulus of elasticity terms cancel out, and we're left with minus mz over I. Like I said, in a lot of mechanics materials books, the most modern ones, they would write this as minus my over I, but they use a slightly different coordinate system. The last thing that we want to do is we want to take a look at deflections. And from taking a look at our deformed beam, now we can relax the constant moment to a moment that changes with position x. So there can be various local radii of curvature. Let's say if we were on this particular spot with some radius of curvature here, along a certain length of beam, we have a certain change in vertical displacement. This would be the distance dx, and the vertical displacement we're going to call w. If we look at the angle that's formed right here, the tangent of that angle is dw by dx, and if theta is small, then the tangent of theta is approximately equal to the angle theta, and the slope of the beam is dw by dx, or we can say that's w prime. Last thing that we'll draw upon is the curvature relation from calculus. Which states that 1 over a radius of curvature for a function is equal to the second derivative of that function with respect to x, divided by the quantity 1 plus the first derivative squared, all to the 3/2 power. Based on our previous assumption that dw by dx is small, much less than 1, when we square it and add 1 and take the 3/2 power, this 1 over the radius curvature term becomes just the second derivative of that deflection with respect to x. So if we go back to our moment curvature relationship, and 1 over radius curvature is equal to w double prime, so we have m is equal to ei w double prime. Now we can do a little bit more work with this if we want. This is enough. If we find the moment equation and if we integrate it twice and apply boundary conditions, we can find the deflection w for the beam. But if we want, we can write this in terms of a distributed load. We know that the shear force in the beam is equal to the derivative of the moment equation with respect to x. We know that the distributed load is equal to the derivative of the shear force in the beam with respect to x. And because of that, then we can write this as the second derivative of m with respect to x. So our equation then becomes if we take two more derivatives of this, we have ei w to the fourth derivative is equal to the distributed load, or ei fourth derivative of w with respect to x to the fourth is equal to that distributed load function, which we could put all the w terms on one side, and we basically get our fourth order differential equation. It's a fairly straightforward one, but it has our distributed load divided by our E and I. Now the last thing I want to mention is for a rectangular beam, where this is the dimension t, and we have some base dimension right here. The moment of inertia is 1/12. That base times that height cubed. And so then we can write this as this fourth order differential equation equal to P naught over E. We'd have a 12 on the top and a B and T cubed on the bottom. Now the reason why I wanted to do that for the rectangle is because we'll see a very similar equation a little bit later on for plates. We want to compare and contrast the amount of plate stiffness, but here we have to the beam stiffness. But here we have a material property term, our modulus of elasticity. Here we have a geometrical term, our moment of inertia, and the last term is our load. So the deflection of a beam depends on how stiff the material is, how stiff the cross-section is, and how much load we put on it. Right, so I'm going to stop this one here, but hopefully the next one will start into our plate analysis.